Hello everybody. In this presentation I want to say a few things about policy iteration. But before we do that, let's take some stock and take some overview here. So reinforcement learning is all about policies. So a policy, again, is sort of like a guide. It's like a compass, if you wish. You're in state, some state, where should I go? And so the policy will tell you, oh, well, why don't you go up? Or, well, if you're in this state, you really ought to go left. Those sorts of things. And by the time we're all done, we're going to look at 3 different ways to generate policies. So we already looked last time at value iteration, where we repeatedly recalculate utilities until there's no significant change left, and then we read off an optimal policy again using our stochastic transition function. Today, excuse me, we're going to be looking at policy iteration. So in policy iteration, you'll like this. We start with a random policy, and then we improve it until there are no more changes. And then next time, we're going to look at Q-learning, where we start with nothing, and we're just going to wing it. Love it. So again, value iteration, we determine the values of each state through an iterative process. We start with value 0 for all states except for the absorbing states, and then we iterate, calculating utilities until no significant changes occur. And at that point in time, we return the utility matrix containing the values for each state. That's how they represent the goodness of them. And as you know, based on what we covered last time and the demonstration, that the absorbing states will radiate out their goodness, if you wish. Based on the utility matrix, we then determine an optimal policy by looking at all possible actions and using our stochastic transition function to select the action that leads to the highest utility value. There you go. So now let's have a look at policy evaluation. And this is sort of like the key and pretty much only slide that we need to be concerned about. So what we do is we start with a policy, and a random policy, just to make up for each state. You look at the possible actions, you just pick one at random, just almost like genetic algorithms, right? And then what we're going to do is we sort of evaluate this, say, randomly generated policy. And what we're going to do is we're going to calculate the utility matrix. Ta-da! And so let's understand this formula. Again, they're very, very similar across certainly value iteration and policy iteration. This here is the key thing. So we generated some sort of policy. So let's suppose it was created randomly, and we call it pi I at state I. So the first one, right? So what we're going to do is, in order to evaluate the utility or to calculate the utility matrix, we look at a certain state S, and we sort of say, hey, what's the policy saying I'm supposed to be doing? So this will give us an action, right, in state S. So again, we want to evaluate the goodness of this policy, the utility of it. What we're going to do is we are then using our transition function like before. We're going to look at the probability that we're actually going to be in state S prime. Okay? Again, action, state, looking at our transition function, the stochastic transition function. What is the probability that we're in state, up or the one above it or below it? And again, we look at the utilities as we have them right now. So what's the utility of the state that we're actually ending in for each of these possibilities? We multiply that with the discount factor. Again, let's suppose it's 0.9 at this point in time, and we add the reward to it. Ta-da! Our utility. Okay? So there you have it. We're now going to have a utility matrix. And so now what we're going to do is we're going to improve it. Okay? Now again, notice that initially the utilities are kind of like empty, right? They're all 0. So initially what we're going to do is this all ends up to be 0, and we just sort of have the rewards. So the first time around, as you will see, there's again this sort of radiating effect from the absorbing states. And so the absorbing states will sort of eventually provide some really high utilities, the non-absorbing states, some very low utilities, and this information will eventually radiate out. I have a little bit of a demo here in a moment. All right, so now policy improvement. So what we're going to do is we now calculate a new policy. So now we're sort of using the information that we have to determine a new policy. And so notice that with value iteration, We ran some loop until nothing else changed. Then we read off a policy. Over here is we come up with a policy, we evaluate it, we improve it. Evaluate, improve it, evaluate, improvement. So both of these steps are part of this loop until nothing else happens. So what are we going to do? Well, we have this policy, right? And so, again, based on this policy pi, we are asking what action should I take in state S? And we're in state S. We're going to look at the, the transition function. There's an S prime missing over here. I'll put that in afterwards. And we're sum up the utilities according to the current policy. So notice this is very, very similar to what we have over here. As a matter of fact, it's exactly the same, except that we're missing these two components over here. So now we're peeking a little bit, see, looking over the neighbor's fence, looking at the grass, see whether it's greener on the other side. So saying, well, I have options. What if I take, let me look at what if I go up, what if I go down or east or west. So we now look at all the actions that are actually available to us, not just the one determined by the policy. And we, again, look at our transition function. We look at, where can I go, where can I end up? And we look at the utilities. Again, it's the same values as these over here. But over here, we're saying, maybe I can do better than what the policy says. And so if, actually, we can do better, then that's what we'll do. So we'll look at the max, which one is the max over here. So I'm sorry, we're saying if there is a better way, if there is an action that gives me a higher expected utility, so we'll look at the value over here, then I will take that action. So this is the argmax over here. So again, what we're going to do is notice that this one here is exactly the same as this one here. So we're going to say, okay, well, I know there's a better value, so which one was it here? And so we're going to look at that action, and that's going to be our new policy. For state S, we're going to pick the one that's actually better, if it exists, than our current policy. There you have it. So might seem complicated, but it's actually fairly straightforward to implement because there's so much repetition over here, right? I mean, you're going to reuse certain formulas all over again, or at least cut and paste, copy and paste. So here is the algorithm. What we have, what I just explained, is this one over here. So this is from the Russell and Norwich. And notice that this loop here goes until nothing else changes. So as soon as one of them changes, then we will go through the loop one more time. That's it. So it might be best to have a little bit of an exercise. So what I have over here is, again, our own world. I have a partial policy. So over here, suppose we randomly or through some other reason determine that, oh, well, the initial policy should be to go up. Now, as you know, we really ought to go right. And so what I ask you to do is use these two formulae or expression to do policy evaluation and then policy improvement. So I ask you to calculate the utility of this value over here, and it might be helpful to also calculate the utility of this one and the utility of this one, and then afterwards do policy evaluation. So see whether there is a better policy than going up. So just do that just to get comfortable with these two ways of doing things, and that'll be a good exercise. So the sheet is posted for today. Just print it out, calculate it, and see what you come up with. I mean, I don't want to give too much of a spoiler here, but you kind of should assume that we eventually will go right. All right, so what I have here is I coded this thing up a little bit. And what I have is what is that, 4x3 world. This is an absorbing state. It has a reward of 1. All the other states, the rewards for making a step is minus or 4 like we have before. And so what I did over here, I didn't have a random policy. I just have a really bad policy. Rather than going right or up, I always go left, right? And so I go away from this one over here. So the question is, can we actually get the right policy? So let's have a look. So here, what I do is I have this random, or this policy, and then I evaluate it. So these are the values. And then based on that, I come up with a new policy. So notice that right off the bat, over here, we're making the right move. Okay, and over here, we're making the right move. Again, I don't have a negative absorbing state over here, so this one just happens to be not a bad move. So they all changed. Why that is, so part of the reason they change is because of the way I set up the if statement when I do things. But the important thing over here is, notice that now, when we evaluate this policy, we get these values. So things start propagating, right? I mean, especially these two here are important ones, so they propagate. So now, based on that, I come up with a new policy. Again, so notice the difference over here is this one now goes right. Again, this one really doesn't matter whether we go right or up. And so we now sort of like have really good policies over here. We also know that these are good policies, but just like see what happens. So the key information really is this one over here. Notice that just like with value iteration, these values propagate. So we now go all right. So rather than going up, notice going up would be silly because we stay in the same spot with 80% probability. So this one finally changes. Again, this one changed to the right. This is a much better idea because if we weren't keeping up with 10% probability, we would be going to the left. So it's really much, because we can't go backwards. That's not part of our transition model. So going right is actually a much, much better idea. And so then over here, we have a change over here where we go right. And there we have a change where we go up. And then we finally go right. So I simply ran this thing for a couple of, no, I ran it until there were no more changes. So that turns out to be 7 iterations. So there you go. The key thing really, the key takeaway is look at how the information got propagated, right? It's not value iteration, but we sort of like got a sense that we eventually came up with a good policy by this iterative process of evaluating the policy, changing it based on our evaluation, and just until there are no more changes. Alrighty, folks, that's it. I'll talk to you next time. Bye.